This resource is the first in a three-part series on solving triangles, or finding missing information for a triangle given some combination of side lengths and angle measures for any triangle. Part 1 considers the law of sines. We define the law and provide the situations to which the law best applies. We look at an example of each case. Part 2 considers the ambiguous case, where the provided information allows one solution, two distinct solutions, or no solutions. We consider examples demonstrating each case. Part 3 considers the law of cosines. We define the law and suggest its best use. We look at examples for each case. In another resource series, we defined the trigonometric ratios sine, cosine, tangent, secant, cosecant, and cotangent as methods to relate the lengths of the sides of a triangle and the measures of the angles of the triangle. However, those ratios required the triangle be a right triangle. One method to relate the sides and angles of any triangle is the law of sines. The law states that the ratio of the length of a side and the sine of the angle opposite that side is a constant for any triangle. Suppose we call the angles of a triangle capital A, capital B, and capital C, and little a, little b, and little c the lengths of the sides opposite those respective angles. Then another way of defining the law of sines is that the fraction little a over the sine of capital A equals the fraction little b over the sine of capital B equal to little c over the sine of capital C. This law is very useful in solving triangles, or finding the missing sides and or angles if we know some lengths of sides and angles. In fact, we solely use the law of sines in the cases where we know two angles and the length of one side, whether the side is between the two angles or not. How do we find these missing measurements? Let's find out. Suppose you know two angles in a triangle. Remember that the measures of the angles in a triangle always total 180 degrees. So we can add together the two measures we know and subtract that amount from 180 to find the measure of the third angle. Now that we know all three angle measures, we are set to use the law of sines to find the missing lengths. We will do the same process twice, one time for each missing length. First, set up your ratios, length of side over sine of the angle. Because we have a proportion, or a fraction equal to a fraction, we can cross multiply. We will divide that product by the other piece of information that we know. This gives us our missing length. Let's look at a couple of examples. Suppose we have the given triangle. We know that angle A is 41 degrees, angle B is 43 degrees, and the length of side AC, or little b, is 15. Note that we know the measures of two angles and the side that is not in between the two angles, which is the angle-side setup. We need to find the measure of angle C and the lengths little a and little c. How do we proceed? First, we want to find the measure of the missing angle, angle C. We have angles of 41 and 43 degrees. All the angle measures add to 180 degrees. So we add the angles we know and subtract that total from 180. This leaves 96 degrees for angle C. Now we can use the law of sines to find a missing length of a side. First, we will find little a, the length of the side opposite angle A. We have a completed ratio, as we know both little b and the measure of angle B. This gives us our first fraction, 15 over the sine of 43 degrees. We set that fraction equal to little a, the length we are finding, over the sine of 41 degrees. We cross multiply the 15 and sine of 41 degrees, and also little a and the sine of 43 degrees. To solve for little a, we would divide both sides by the sine of 43 degrees. However, we can do all this work in one step, as shown. This results in A equal to 14.43. Now we can find our other missing length. Exactly as before, we set up our ratios. We use the original given information of 15 over sine of 43 and set that equal to little c over the sine of 96 degrees. Cross multiply and divide. We find that little c equals 21.87. Note that this is the longest side, and it is opposite the longest angle. This will always be the case. The bigger the angle, the bigger the side opposite it. Let's look at another example. In this example, we know that angle A is 29 degrees, angle B is 53 degrees, and the length little c is 25. This time, we have two angles and the length of the side between those two angles, or the angle-side-angle setup. We start by finding the missing angle measure. We subtract 180 minus the sum of the angle measures we do know. This leaves 98 degrees for the measure of angle C. Now we can use the law of sines to find a missing length. Our complete ratio is length little c and angle C, so we have 25 over the sine of 98 degrees. We set this equal to little a over the sine of 29. Cross multiply and divide. We find that length A is 12.24. Now we will find our other missing length. We set up our proportion, 25 over the sine of 98 equal to little b over the sine of 53. Cross multiply and divide. We find that length B equals 20.16. The law of sines states that the ratio of the length of a side to the sine of the angle opposite that side is constant for any triangle. We use this to set up proportions to find missing lengths when we know more about the angles in a triangle than we know about the lengths of the sides. Once our proportions are set up, solving is relatively easy. We cross multiply and divide. Many real-world situations actually use the law of sines for solving. These include surveying, cell phone triangulation, and situations where movement changes angles of elevation, like when a ship approaches harbor. There is one case where we will still use the law of sines exclusively, but we know more information about the lengths of sides than the angle measurements. We will discuss this situation in the next resource in the series.